Welcome to Brain Vision.
We start with the wave function and we're going to substitute it into the Schrodinger equation, which in this case is for the harmonic oscillator. So we'll need to take the first and second derivatives of the wave function. Taking the first derivative gives us a derivative with two terms because we had x times the exponential function. Next, we take the second derivative and we obtain a second derivative with three terms. This is due to the first term in the first derivative having only one term, but the second term in the first derivative having two terms. And notice that the first two terms of the second derivative will combine to have a coefficient of -6. So with this in mind, the second derivative can actually be written in a factored form to give the following expression with the original wave function factored out. This can then be substituted into the Schrodinger equation as it only remains to determine B in terms of the parameters in the problem. So here we're going to be writing two equations. So far we have one that is written in terms of constants times the wave function. So this was obtained by taking this first term right here and this constant term times the wave function on the right hand side of the equation and equating them. Next, we're going to have another equation obtained in a similar manner. Where we note that in this case, what was done is we take x squared factors multiplied by the wave function, and we combine them, or in this case, we add them together to equal 0 because on the right hand side, we don't have any x squared factors multiplying the wave function. So we have a b squared x squared factor here, and we've got an m omega squared x squared factor right here, and these have to add up to equal 0. Whereas our first equation, once again, was -6b times -h bar squared over 2m, which is right here, must equal e ax, etc., because these two terms must be balanced. They must equal each other in order for us to have a solution. So these are two equations we obtained, and from this we can obtain two unknowns. Namely, we can obtain b, and from that we can obtain e. So once we get a value for b, we then get a value for e, and proceeding in that manner, we get that for simplicity, we'll let the wave function and x squared cancel from both of these equations. And immediately, we can write e in terms of b as 3h bar squared b over m. And then we can write b squared as this quantity. The negative, there's two negative signs that multiply each other. So really b squared is just 1/2 m omega squared times 2m over 4h bar squared, which will of course simplify. and that simplifies to m squared omega squared over 4h bar squared. Taking the square root of that gives b equals m omega over 2h bar. So with these two equations, we can combine b and e to get an expression for e. E is then equal to 3h bar squared over m times m omega over 2 h bar. And then we have cancellation that occurs, and we get E equaling 3h bar over 2. Now this is actually the energy for the first excited state, because you can write this as the 3 halves as 1 plus 1 half. So this is the first excited state of the harmonic oscillator. And with having determined a proper value for B, we can see that we have indeed a solution of the harmonic oscillator, and we see also that the wave function properly factors on every term of the Schrodinger equation where it should belong with the value of B that we have determined.